We are now going to talk about resistors in parallel. Back when we learned about capacitors, we learned how to identify capacitors in parallel and capacitors in series. Now, I told you some simple rules for combining down circuit elements, and some of those still apply here, but something that you're going to sometimes see is more than two combined in parallel, and that's what's happening here. So parallel is indicated by a junction. And one thing to note here is that we actually have three resistors that are all in parallel with each other. How you can identify this is that the top of the resistor is all at the same potential. The bottoms of the resistors are all at the same potential. That indicates that the delta V across them are all equal, and that means they're in parallel. If I started to add another resistor somewhere in here, that would actually break this because you would have a change in potential across that resistor as well. But as long as you have the same potential difference across every single resistor that you're working with in a chunk, you would say that they're all in parallel, and that's the situation we have here. You are going to frequently want to combine resistors down into one equivalent resistor in order to analyze a circuit. And again, we said that our potential difference is the same across them. The current will be different through them if the resistance is not the same. So keep in mind that the potential difference is the same, and due to Ohm's law, if the resistance is the same, that does mean the current is the same. But from Ohm's law, V equals IR, we know that if delta V is the same for them and I is higher in one, that means your resistance is lower in that one. And remember from Kirchhoff's junction rule that whatever this current is basically splitting, and so you have to sum up I1 and I2 to equal the current that you get on the at the ends of these junctions. So keep that in mind. So I'm not going to go through the specific derivation, but when we combine them together, it has this reciprocal form. And you actually saw this for capacitors when they were in series. So something kind of tricky to keep in mind is that we can talk about parallel capacitors and we can talk about parallel resistors. They physically look the same in the circuit when we identify them as parallel, but the way we combine them together is actually opposite. So this is somewhat what the equation looked like when you were combining capacitors in series. So be careful. So the rule is that all of the resistors must have the same delta V, again potential difference across them. The currents through them might vary. And to make this equivalent resistance, you do the 1 over all of the resistances that you're dealing with, and then to the -1. So another way you might see this written, perhaps if you only have 2 to worry about, is that 1 over your equivalent resistance equals 1 over one resistance plus 1 over the other resistance. Remember that the rules of algebra say that this is not the same thing as equivalent resistance equals the resistance of one plus the resistance of the other. So be careful to keep in mind that you can't just flip these all upside down. That's not valid algebra. So this is the idea of actually combining resistors together in parallel. Not that hard as long as you don't make an algebra mistake and as long as you recognize correctly that they're in parallel. Now, frequently we're going to have more than 2 resistors to think about, and so quickly here I'll do an example in the next video thinking about more complicated circuits.